representative volume element we are trying to find out. Okay, so I'll take the example of composite. So you have a composite in which there are fibers, randomly distributed fibers. I'm drawing it like evenly, but they are randomly distributed fiber. Okay, so I need to know the property of whole composite. This whole composite. Suppose this is a very big composite. These walls are like infinite wall. I have taken a small area inside this composite. So why do I need representative volume element is because I want property of some small section of this whole composite, and if I measure the property of the small section, and that property should represent the property of whole uh, big composite, big or whatever size you have. So that's why we use this name as representative volume element. And even though we are measuring in a small area, but we still call it as volume, because these material properties are not associated with areas. These are associated with, ultimately they are associated with volume. So that's why we call it representative volume element. We do take consider the z direction inside our calculation, but we don't see it. We assume that in z direction the properties are homogeneous, which generally happens in case of composite. In this case also the properties or the variation in this direction is not there. And even if they are there, the gradient of the properties in z direction is not as much as the gradient inside this area. So that's why there is no problem. Even if we measure in an area, we can still call it as a representative volume element. Now the fundamental is, I'll just take an example. So if I take the properties of a point, a small point, in suppose in one of the fiber, this I have taken a point here. So this point by default it will be stronger. So this will have high strength and low ductility. This will have stress strain, something like this. I am assuming that I am loading this in this direction or in this direction, but these all, the whole area is under uniform loading. This is my assumption before doing any analysis, before making any calculation further. This assumption should remain in your brain that the loading is uniform at all point. Otherwise there is no point. If I load this point as, suppose, greater strain rate or greater displacement, and this point is at different condition of loading, then I cannot compare them. So to have a comparison, to have a fair comparison, I need to have a uniform loading across all the points. So once you have a uniform boundary condition in all these points, then if you construct the stress strain curve of this fiber element, it will look like something like this. An example. And if I take this point here, pp, this is suppose p1, this is p2. So this will look like this. So you will have more ductility. So this is p2, this is p1. You will have more ductility and you will have less strength. This is suppose s2, and this is let's take e2, and this is s1, and this is e1. So these are the initial difference of the properties of matrix and fiber. But we want the properties of this whole like aggregate properties of this composite. Okay, so aggregate property, suppose if I take a big volume and if I test the big volume, then that property I can call as uh, properties of the composite. So this, that will look like something like this. So it will have some intermediate, let's say s P I'll call, or SC, composite, strength of composite, and EC, ductility of composite. So this is the property of the composite material. Now I can call it as a property of a material. Material, the composite itself is a material which is having fibers and matrix, or whatever you put into it. Its constituent could be like n number of constituent can be there, but including all those constituents, I am saying that this is the property of that composite as a material, as a homogeneous material. Although it's a heterogeneous, point wise it's a heterogeneous material, but I am saying this as the properties of this composite. Now moving forward, if I take, instead of taking one point, if I take a little bit bigger area, suppose this big area, which has some metrics and some part of fiber, like fibers are there and number of fibers are there, so some fiber and some metrics. So of course it will not be like this property, and it will not be this, it will be in between these two. It can be here or it can be here, but still it may not represent the actual property. This is where we want to reach out. This is our objective, this is our target. Okay, so we have taken an initial area A1 and we measured the properties on this area, and we suppose we found out that the properties are coming here. And if this area is suppose coming here, that there is no fiber, it is possible that there is no fiber in it, although we have taken a bigger area than a point, but still it may have the whole of a matrix. So the properties may be like here. So these are the chances. Now if we take different areas, here, here, the same size, we are not varying the size, and we are taking different areas, so they will have different variation like this. They will have different properties, all of them together, but we cannot call it as a like representative RVE or RVA. We cannot call it, because you see that if like by calling RVE means, no matter where you take this area, it should converge to a particular property. Suppose this one, I'll draw the new one. So this is fiber and this is matrix. So if I want to have this as my final properties, so if I take an area, suppose this is A1, A2, A3 are different areas, and I'm putting a subscript here, a superscript here, A naught. So this zero represent the size. So initially, suppose I have taken a size of let's take the example of 4 by 4, and if I take the 4 by 4 size, and I see that there is huge variation. If I take this A1, A2 at different locations, if I repeat this area at different location, and I see that there is a huge variation in the overall property. So now I cannot call it as RVE. Now what I will do, I will increase the size. I'll do this A naught. So A naught is little bit bigger. So you have this. So let's say this is A naught, A1, and inside this A110, I can take another like this. They can be overlapping. There is no problem. So I have constructed A1, A2. Sorry, A1 is the size, one, 2, 1, and 3, 1. So these are the four areas. Now if I draw these curve here, they will be like this. 1, 2. It could be overlapping to this one. So you see that this variation has reduced now. So it's getting closer and closer to your actual property of the composite. And if you keep on increasing the size of that area, you keep on increasing the size. If suppose this is my whole composite, which have various numbers of fibers in it, randomly placed, there is no order, If there is order, then it becomes very easy for us, because if you have seen the crystal structure, if we take the unit cell and if we repeat the unit cell, it will represent the whole crystal structure. So then that is your representative volume. You can say that is our representative volume. But they are so nicely kept, they are so arranged that you will not see any deviation from the structure. That structure is well defined, but this is not well defined, this is heterogeneous. That one is called homogeneous, this is heterogeneous. So if you take bigger area, suppose this is your new area at different locations, they can be overlapping. It's up to you. No matter where you take, you have reached an area. Calling it a r, and these are different areas. A naught, this one is, this one is AR1, this one is AR2 and AR3, and this one is AR4. So now if you draw, this is your fiber, this is your matrix, and this is your composite properties. Now you will see that they are coming very close to each other. So all these areas are AR, and different one, two, three, four. They are here. So now no matter where you take this area, no matter where you take this area, you will get this property. So that means that this size R size, this size R, this represent the material property. Material properties. This size, it's very important that this size represent the material properties. And this whole exercise we have done because this material is heterogeneous. Okay, so in case of a heterogeneous material, you take the size, so that if you repeat that size, if you place that size at any location, and if you get the same properties of the material itself, then you call that volume or that area represent the whole material. And that's why this name has come, that representative volume element. So this is the element. The element name is, there is a size component in it. This is the element, and this represent the property of the whole material. So that's why we have given this name as, we call this R as RVE. So this size could be, let's take 100 by 100. Just I'm taking an example. So if you take bigger than this, if you take 120, then 120 by 120, you will still get the material property, right? Because if you have repeated this size and if you are getting this, if you take bigger size, you will, of course you will get the same properties or even closer than that. So that if you take smaller than this, if you suppose if you take uh, r, the small r, 90 by 90, suppose if you have taken 90 by 90, then you will start getting the deviation from this.